So hi, everybody. Welcome to the webinar of today. It's about advanced power electronics courseware featuring HYPERSIM. So I'm going to start by presenting the presenters. And so we have Wolf Peter Jean-Philippe. Wolf has joined OPAL since August 2021. He's senior courseware analyst. Then we have Angelo Shabiye that joined OPAL in August 2023, and he's courseware analyst. And we have Professor Innocent Camois from Laval University. A quick bio for each. So Wolf received a bachelor degree in electromechanical engineering from the Faculty of Sciences, State University of Haiti in 2012, and master's in electrical engineering as well as PhD from Syracuse University in 2015 and 2020 respectively. His primary research interests encompass demand response, modeling wind power generation, and the operation and control of power systems with high penetration of wind energy resources. He's senior courseware analyst at OPAL-RT Technologies, where he leads the development of electric real-time virtual laboratories focused on power electronics, motor drives, renewable energy resources, microgrid control and operation, among other topics. Then Angelo is a junior engineer. He receives a bachelor degree in electrical engineering from École supérieure d'ingénieurs de Beirut, St. Joseph University in Lebanon in 2023. He joined OPAL first as an intern in summer 2022. Then he did his FYP with me at OPAL during the winter of 2023. And since August, Angelo works as a junior courseware analyst at OPAL-RT, where he contributes to the development and maintenance of electric and robotics real-time virtual laboratories. And last but not least, Professor Innocent Camois, he obtained the PhD in electrical university, in electrical engineering from Laval University in 1989. He's fellow of the Canadian Academy of Engineering and an international member of the US National Academy of Engineering. He's currently a full professor in the Department of Electrical Engineering, Tier 1 Canada Research Chair in Decentralized Sustainable Electrical Grid for Smart Communities, and a Distinguished Professor of Power Engineering at Tsinghua University. Previously a researcher at Hydro-Québec Research Institute, IREC, he was the principal scientist of Hydro-Québec Smart Grid Innovation Program and head of Power Systems and Mathematics, directing the Network Simulation Laboratory. An international consultant in simulation and stability of power systems, he's a fellow of the Institute of Electrical and Electronics Engineers, IEEE, for contribution to adaptive power grid control schemes and synchronous generator testing and standards. He's a recipient of 6 IEEE PS Best Paper Prize Awards, 5 IEEE PS Outstanding Working Group Awards, and the IEEE Charles Proteus Steinmetz Prize, and the IEEE Power and Energy Society Charles Concordia Power System Engineering Prize. Dr. Camois is also a fellow of the Royal Society of Canada and editor-in-chief of IEEE Power and Energy magazine. So thank you, the three of you, for being here, the presenters. And I'm going now to go through the webinar outline, then I'll give the floor to the presenters. So there is an introduction to start by. Then Wolf is going to show us the synchronous generator static excitation system. Angelo will be doing the thyristor-based static VAR compensator. Then Wolf back with DC-DC battery storage interface, Angelo with IGBT rectifier inverter systems, and finally also Angelo with uninterruptible power supply systems. Then we're going to open the floor for questions where Wolf, Angelo, and definitely Professor Innocent Camois will be more than happy to answer you. Thank you and enjoy the webinar.
Thank you, Daniel. Hi, everyone. Thank you, Daniel, for the presentation, and thank you for joining us for this webinar. And before we start, I'm going to introduce what is a Courseware. So Courseware is a virtual laboratory, and virtual laboratory can be related to power system, renewable energy, electric machine, motor drive, and so on. And how does it work? So we have a real-time simulation platform. So it can be RT Lab, but in this case, today we're going to focus on HYPERSIM. And the real-time simulation platform going to simulate the model that we're going to study as part of the laboratory. And we have our own OPAL-RT dashboard to design graphic user interface where the user gonna have in front of him a screen, as example like this, where he can manipulate the laboratory and observe the result in real time as he or she do the changes in the system. And how does your courseware run? The courseware can run in a student PC or user PC. So this is what we call a local host. Or it can run in one of our real-time simulator, for example, OP4512, but there are other type of simulator that can run as well that we have available at OPAL-RT. Or we can run it with an external controller that we call OP-8066. Basically, let's say if you are doing a motor drive, you can run the whole system, what we call model in the loop or software in the loop, and the OP4512 alone. Or depending on the application, you can export the controller to a piece of hardware controller OP-8066 and run the rest of the model on the OP-8512. So here I present like 3 different ways we can run the courseware and what are the platform. And for us today, the focus is gonna be in running the courseware on HYPERSIM. So we have it also in AutoLab, but today focus of this webinar is how to run courseware with HYPERSIM. And Angelo and I and Professor Kam are gonna present for 5 different modules that we have developed on HYPERSIM. Before we start in the module in HYPERSIM, I want to quickly give an overview of some of the topics that we cover on the courseware. We have fundamental of electrical engineering. By fundamental, we basically mean fundamental, like the basis, Ohm's law, parallel resistor, series, and so on, transformer. We have power electronics, we have electric motor drive, we have renewable energy courseware, we have electric machine. And today the focus is gonna be on the advanced power electronics that we have developed on HYPERSIM. And what is HYPERSIM and why HYPERSIM? HYPERSIM is basically the power system simulator of tomorrow. So 5-10 years from now, HYPERSIM gonna, as of right now, we are one of the leaders, and HYPERSIM going to be continue to be one of the leaders. And if you want to simulate anything related to power system or power electronics, HYPERSIM gonna be the way to go. And that's why today we want to show some of the capability of HYPERSIM and some of what we can do on HYPERSIM. And some of the example, we can simulate light power system by doing decoupling. We can do HGVC and modular multi-level converter control. It can be used for cybersecurity. It can be used for poaching system and microgrid. And today, the main focus is gonna be on power electronic related application that we're gonna show how we can use HYPERSIM to do that. And some of the things that HYPERSIM, that is integrated with HYPERSIM, we have test view. Basically, test view allow you can run Python script to run multiple scenarios without to do them one by one. You can run the Python script and run the scenario and get your result later. Or you can even use test view to do automatic reporting, plotting your data, analyzing your data, and so on. We also have scope view. Scope view is integrated with HYPERSIM, and it contains mathematical function like that allow you to directly do analysis over the signal that you are studying. You can also do graphical manipulation, so zoom in, zoom out of your data, and when you can analyze offline after you save your data, and you can use scope view to do that. And we also have dashboard. Dashboard is for which is the graphic user interface where you're gonna analyze and visualize your data in real time. So you have scope view where you can save data and analyze after. And you have dashboard that you can use on real time, and you can do control button, tables, and different type of things that we're gonna show later in the demo that we're gonna present in this webinar. Okay, so the first part of the webinar today, I'm gonna start with introducing the lab 1 of this module, which is synchronous generator stator excitation. So in this module, I'm gonna focus on control rectifier, which is a type of the AC-DC converter. So we have an AC input, we're gonna convert to a DC output. So why control rectifier? It's because the application we are focusing on is for if what we wanna do bidirectional power flow. So if one of the example is, let's say you have a synchronous generator, you wanna excite the field winding of this synchronous generator. So control rectifier instead of diode rectifier is is more applicable to that. To do so, that's why we're gonna consider control rectifier for static system, excitation system. And we're gonna operate the rectifier in two ways, steady state and transient. And we're gonna see how does the system behave and what, or can we show the result in HYPERSIM and using dashboard. So as I mentioned, one application of the control rectifier is for excitation system, as we can see here. So if you consider any system as a whole, the twistor rectifier is gonna play the role of the AC/DC conversion for the excitator block on the excitation system so that it can provide DC voltage to the field winding of the synchronous generator. And the circuit that I'm gonna show the result that we are simulating is we have a hydro generator, 13.8 kilovolt, 60 hertz, and light to line we have 57 volt. That is that's supplying voltage to the a full bridge rectifier. We have 6 rectifier here, and the output gonna excite the synchronous machine field winding. So we're gonna analyze the operation of the bridge rectifier in steady state, and we're gonna see also what is happening if we control it in transient state where we are imposing a current and see how does the system behave if we are manipulating in control loop or versus open loop. So here I'm gonna play the video. So the video is playing, I'm gonna explaining. So this is the circuit we have in HYPERSIM. I'm not gonna focus on the detail on the circuit itself. I'm more on the results of how we can manipulate a dashboard and to show the results. So as I'm showing here, we can open dashboard directly via HYPERSIM. And this is the circuit again. We can see, if I go back here. So here in the circuit, we see the twistor bridge that we are analyzing. And this is the dashboard. On the dashboard, on the top, we have the circuit parameters. So we have the transformer voltage. Circuit parameters is parameter that we can modify as the simulation is going on and observe how does those parameters affect the results. In terms of control, we can operate the system either on open loop or closed loop. And at the same time, we can save data for offline analysis by just clicking on this button. And we have different type of scope to visualize the results of the simulation that we are performing. Also, there is a help section which kind of summarize the system to give the user a brief understanding of the system that they are simulating. So here I will start the operation. I'm gonna start showing the results. Simulation is starting. Gonna move to showing the results. Okay. So here, at a firing angle of 0 degrees, so this is how the system behave. We see the rectifier output voltage. This is the input 3-phase voltage that we have, and this is the DC current. So this is for the firing angle of 0 degree. What if we put a firing angle of 15 degrees? I'm gonna change 0 to 15. And for 15 degrees, we're gonna see the shape of the signal are changing because we are imposing another firing angle at the input of our control rectifiers. And where we can mainly see the difference again is if we analyze the power factor, because we know the power factor gonna be it's 0.955 cosine alpha. So as alpha increasing between an angle of 0 to 90 degrees, the power factor gonna be decreasing. So at 15 degrees, we have a power factor of 0.91. And if we go back to 0 degrees, we're gonna see we have a power factor of 0.995. And this, we can observe it in real time as we are doing the changing in the simulation. So I go back to 0 degrees and we move from 0.915 to 0.955. And this was mainly operating the system in steady state because we are on open loop. We are not imposing any current to control the firing angle. So we are imposing the firing angle directly ourselves. Now, if we move to closed loop, the firing angle gonna be an output of a closed loop control. So we have two scenarios that we can simulate. So I'm gonna trigger to show you the result of scenario 1. So in scenario 1, what are we doing? We're imposing a reference current from 0 to the nominal current of the system that we are studying. So from 0 to 694, and we are seeing what does the firing angle that we're gonna apply to the rectifier is answering based on the control that we're imposing. And if we move to scenario 2, where we're going to do the opposite, going from the nominal current to 0, and we're gonna see how the system responds to what we are imposing. So I'm gonna let it play. So we're gonna move from scenario 2, and we're gonna see how the system responds when we move from nominal current to 0 as, and this is the response. So from here, we go from the nominal current to 0 as a reference current, and the measured current is following it, and we can see how the firing angle gonna be. So that's why we say it's not steady state. We can see there is change in the way the firing angle is jumping from one value to another before it's stabilized to a final value based on the current control that we are doing here to generate the firing angle that's gonna drive the full bridge series rectifier that we have. Now I'm gonna pass it to Angelo for the next part of the presentation.
Thank you, Wolf. Hello, everyone. So I'll be talking now about the second laboratory. So we're talking about the thyristor-based static VAR compensators. The static VAR compensators consist of a thyristor-controlled reactor as well as some filters that are connected to it. So what's the thyristor-controlled reactor? It's an AC controller. It is an AC to AC converters, which controls the magnitude of the fundamental component of the AC waveform, while maintaining the frequency of the signal of the input. It is also a reactive power controller, so we can change we can change the reactive power by changing the value of alpha of the firing angle delay alpha, and we can also control it operates with phase control. So in steady state conditions, it acts as an inductive reactance dependent on the fire angle, and but the TCR introduces harmonics to the source. So while using the thyristor-controlled reactors, we have harmonics that are being introduced. That's why it's necessary to mitigate, to use mitigation techniques by adding filters to it. And that's why in our application, we use it in an application like the static VAR compensators, for example. So this is a single line diagram of the static VAR compensator, the one that we are working on in this specific courseware. So we have a thyristor controlled reactor in 20 MVA, which is connected also to a fixed capacitor, 10 MVA, and to two thyristor switched capacitors, 20 MVA. All those are connected to the output of a transformer, which is rated at 13.8 kilovolts. Now we're gonna see a video demonstration of how the circuit is being simulated in HYPERSIM and how we can control it using also dashboard to observe the results. Hello, my name is Angelo. In this video, I'll be showing you how to use the thyristor-based static VAR compensator courseware, electric courseware. As you can see, this is a circuit that is built on HYPERSIM. We can start by going to dashboard and then going to help in order to see the circuit that we are working on. You have here all the details of the circuit. You can also see the circuit on the first panel here. So as you can see, we have an AC grid, which is connected to a transformer, which is then connected to the thyristor controlled reactor and to three components that are used as filters, the thyristor switched capacitor 1 and 2, as well as a fixed capacitor. They are working as the 5th harmonic, 7th harmonic, and 11th harmonic filter. So the objective of the static VAR compensators is to have an output voltage here that can be controlled. So we can select change the output voltage based on the delay in degrees that we are inputting for the thyristor controlled reactor. So here we select the TCR phase delay. We select the phase delay of the thyristor controlled reactor. We will have a voltage output based on this delay, as well as a reactive power consumed by the thyristor controlled reactor based on this alpha, this angle. And if we change alpha, these values will change. But the thyristor controlled reactor will introduce harmonics to the grid. In order to eliminate these harmonics, we will need to add the different filters that we added here. So I'll start by running the simulation. In this case, I have an angle of 120 degrees. So as you can see in the scopes on the output of the transformer, the source current has introduced harmonics. It is not sinusoidal. And so we can see the source current, source voltage, and source reactive power. If we go to the thyristor controlled reactor, we can see the inductor voltage, which we have controlled here. We can see the fundamental of the voltage using the harmonics analysis later on, because that's our main objective, to control the voltage fundamental voltage. And we can see the consumed reactance. We can change the value of the angle alpha here, 160, let's say. And we can see how this will affect the different results. Now, in the transformer, as we said, we have the harmonics that were introduced. So in order to reduce these harmonics, we start by activating, using these switches, activating the different blocks that are connected, different filters. So we can activate the 5th harmonic filter, the 7th harmonic filter, as well as the 11th harmonic filter, and see the result. Now let's go to harmonic analysis. Using scope view in HYPERSIM, we can see the harmonics analysis. So we click on function, we select harmonic analysis, harmonic. Let's go for the source current on the output of the transformer, and the first 1 year harmonics, let's say, add function, run. Okay, so here I have already the filters are activated. Let's deactivate them. So I'm gonna deactivate the filters, run. Okay, as you can see here we can see the harmonics. And let's say we want to deactivate the 5th harmonic, so 300 Hertz. Here, want to filter it out. Okay, as you can see, we filtered out this value. So thank you for watching, and if you have any questions, don't hesitate to ask me.
Thank you, Angelo. I'm going to move to the next part, which is lab 3, which is DC battery storage interface. And this, we're going to focus on a 2-quadrant DC-DC converter. Why 2-quadrant? Because, again, we want to do bidirectional power flow. So where we can, for example, in this application here, if we want to charge or discharge the battery, so we want to be able to, the current to flow in 2 directions, going to the battery or from the battery. So that's why we're going to focus on 2-quadrant DC-DC converter. And the application going to be for an uninterruptible power supply. So where we're gonna see if we are operating this converter in bulk mode. So we're gonna charge the battery. And if we are operating this converter in boost mode, we're gonna discharge the battery. And what is the circuit that we are looking at? As I mentioned, it's a UPS system, but Angelo gonna be focusing on the rectifier and inverter part, and I'm gonna focus on the DC converter part where we have to charge and discharge the battery. And the circuit that we are studying is here. So we have the bidirectional DC converter here with two IGBT that we need to control. And depending if we are operating the system in open loop or closed loop, we can, in closed loop, we are imposing a voltage reference that's gonna be giving us a current output that's gonna be generating the pulse to drive the IGBT inverter that we have here. Again, as I mentioned, I'm gonna be focusing on the DC side of it, boost and buck operation. And the next part, we're gonna be focusing on the rectifier and inverter. And finally, we're gonna put everything together to show the result of simulating a UPS system in HYPERSIM. So the first part of this video is when we are operating the DC battery and on buck operation, basically. So we have the UPS, if I go back here. So it's two scenarios. If the primary input is operating as normal, so the UPS is in normal mode, so we're gonna be charging the battery. So if the primary input failed, so the UPS gonna be operating in emergency mode, so we're gonna have to discharge the battery. So if you have the three-phase input, we are charging the battery. If it's failed, we are discharging the battery. Basically, that's what the UPS system does. And again, here, the focus is not much in the detail of the circuit because it's more, or we implement the circuit. If you have a question about the circuit, and we can ask during the webinar. So this is the dashboard of the circuit. At the top, we have the circuit parameters. We can use the switching frequency, the duty cycle, and the battery voltage. Here, initially the battery volt is at 400 volts, which is the low end. It's no load when it's totally discharged, and because we're gonna be in buck operation mode, so we have the AC input working well. We're gonna be charging the battery, and we're gonna see what are the relation when we are in buck mode between voltage and duty cycle and so on. And again, we can operate the system in open or closed loop. As always, we have a help available in the panel that describes the circuit that we are simulating. And here, I'm going to just run the model. Just skip the step to show the results. Okay. So here for a duty cycle of 0.612, why is 0.612? We impose this duty cycle so that we have an output voltage of 700 volts. And if you do the formula available online or in our description for the Courseware, you will see that based on the input voltage you have here in the duty cycle, all the value that we have here are matching the theoretical result and matching the simulation result that we should be obtaining for a buck boost converter, for a buck converter. So basically, we know if you do 400 over 1 minus 612, you should be close to 700 volts. And we can move to look at some of the results. If we go to scope 2, so here we are showing, let me go back to scope 2. In scope 2, we are showing based on the duty cycle, or does the output voltage is switching between from maximum to 0, and from there we are measuring the mean voltage that we are obtaining from the switching of the 0.612 duty cycle. And later on, I'm gonna move to another duty cycle and show what is the difference if we have a high duty cycle or a low duty cycle. So all of this here, I'm operating in open loop, so basically steady state. So what happens if we operate in closed loop? I'm gonna trigger closed loop control. So I'm gonna imposing a reference current, and this reference current control loop gonna be the one outputting the duty cycle that we need to provide to drive the IGBTs for the boost converter. So here I'm imposing a reference current from 0 to the nominal current, and if you observe the error, we see that the control works properly because it's converged towards 0. And this duty cycle, this current control loop generates this duty cycle that we have, based on the closed loop model and control, this duty cycle gonna be the one that generating the pulse that drive the two IGBTs that we have on the converter that we are analyzing. And I'm gonna move to the last part of it here for when we are in bulk mode. In bulk operation mode is, instead of imposing 0.6 value to cycle, what if you impose 0.5? So if we import 0.5, we see we have a mean output voltage of 300 because the input voltage is 700. So 700 by 0.5 almost give us 350. So input voltage, output voltage. So we are almost at 350 with a duty cycle of 0.5. As we can see, the theoretical formula match the simulated results. Now I'm gonna move to when we operate the DC battery storage as boost operation mode. So basically here is the scenario where you don't have the AC input and when you wanna be charging the battery. Again, this is the circuit and Simulink. The focus is not to implement the circuit in Simulink, is to show the manipulation and the result and dashboard of the circuit that we are studying. And similarly to the previous one, oh, here I'm still in bulk mode. Okay, now this is the one for the boost mode. At the top, again, we have the circuit parameter. The panel are very similar for this two lab because it's mostly the same circuit, but we are operating in different conditions. So I'm gonna run the simulation and start showing the results. Okay, so from here, we have a duty cycle of 0.367. So why we need this is because we want to impose a DC voltage of 700 volts at the DC side of the UPS. So for this duty cycle, and if you do the theoretical calculation, you will see that the theoretical calculation are matching the simulation result that you're obtaining here if you have a boost converter. And again, based on this duty cycle, we are seeing orders. The input voltage is switching from one value to 0. And from there, we can measure the mean output voltage that we are displaying in this display here. Same thing, we can observe the distinct voltage. That's the focus is to maintain that 700 volts. This is the mean DC current. We also compute the power. We can do harmonic analysis using scope view as Angelo showed us earlier. And the system can also be run in closed loop control. So open loop, you are imposing the duty cycle directly. In closed loop control, the duty cycle is flowing from in this case, from a 2-layer control. First for we have a voltage loop control and then a current loop control, and that's gonna give us as output the duty cycle that we need to drive the two IGBTs that we are using in this boost converter. So I'm gonna apply closed loop and then trigger to see the result. So we are imposing a reference voltage from 0 to 690 volt, and we are seeing the measure value following it. And the error converges towards 0. That's when the control is working properly. And if you move to the other tab, I'm gonna move to the other tab to show the current loop and the duty cycle. And so from the current loop control, we see that the measured current is following the reference current. And from this 2-layer loop control, this is the duty cycle that we are obtaining from when we are operating in transient mode, basically in closed loop control of this boost converter operation if you want to charge the battery for your UPS system. And similarly, at the end, we can see for different value of the cycle, what happened if we impose another cycle. So 0.267 was here initially because we wanted to maintain it at 700 volts, but the system can be used to study a boost converter in itself. So the student can use different duty cycle and plot the relationship between the duty cycle and the distinct voltage, mean input voltage, battery voltage, and so on. So this is the demonstration for the DC-DC side. I'm gonna leave it with Angelo that's gonna present the later part of the webinar. Thank you.
Thank you, Wolf. Now let's go to the fourth laboratory. So we have the IGBT rectifier inverter systems. So I'm gonna first talk about the inverter, then about the rectifier. So we have the three-phase two-level inverter. Like any inverter, the input is a DC voltage and the output is an AC voltage. In this case, it is a six-switch two-level output inverter. And the voltage is regulated at 480 volt, whatever the operating mode. So in the different cases, for example, in the circuit of the UPS, like Wolf was mentioning, this is a second part of the UPS circuit. We have Wolf focused on the DC battery storage system, and this is the rectifier inverter system. So whatever the operating mode in that circuit, the output is 480 volts, and it is connected to a load through reactance. As you can see, the circuit on the right. Okay, this is, for example, one of the things that we can test during the courseware while using the simulation. We can see how the fundamental RMS line voltage varies with while varying the modulation index MA. So for MA less than 1, the fundamental RMS line voltage increases proportionally with the modulation index. Like over modulation, when MA is greater than 1, we are in over modulation. The fundamental RMS line voltage does not increase linearly. And now for the rectifier, in our case, we are using an IGBT 6-switch two-level input rectifier. Also, like any other rectifier, we have an AC input and a DC output. The nominal input voltage is 480 volts, but we can it can varies between 430 and 530. This is permitted. And this is something that we can also do in the courseware. It is accessible. We can change the value of the input to see how it affects the output of the rectifier. And it is also connected to an AC grid through a reactance. And in this case, the rectifier is configured with a controller in order to be able to control the output power factor and the output voltage. So we can set the power factors that we want as an output, as well as the output voltage, what is the DC voltage that we want to have. And we can see how it will react. And we're gonna see that in the demonstration in the next slide. Hello, my name is Angelo. In this video, I'll be showing you how to use the IGBT rectifier inverter systems in HYPERSIM. So as you can see, this is the circuit that we are working on. You can start by clicking on dashboards and go to help. The IGBT rectifier inverter systems have been implemented in this case to be used with a UPS system. So this is a UPS system, but for this specific courseware, we won't be connected. We will be working on each component alone. So we will work on the rectifier alone, the inverter alone, with a DC input, and then with a ideal DC input, and then with a DC battery input. So let's go to the panel. So part 1, the inverter, which is connected on a DC input. So we can start by clicking run and selecting part 1. Okay. So after selecting part 1, we can see the output of the inverter. This output depends on the reference of the modulation index. So we chose 0.25, and it also depends on the control types that we selected. So we selected the PWM control. We can go to square wave control as well and see how the output changes. For the output, we have the three-phase inverter output voltage, the line inverter output voltage, the three-phase inverter output current, and the inverter DC current input. So we have the DC input and we have the output. We can go again to PWM. And you can also see the line-to-line voltage here, which is 127 volts, for example. You can change the modulation index and see how the result changes with it. You can also go to over modulation, which is a value greater than 1, and see the results. In part 3 is very similar to part 1, but the only difference is that we are working, instead of using a DC ideal source, we have a battery source, which is connected to a DC converter, which is then connected to the inverter. And we can also do the exact same tests, but in this case, we are using directly the PWM control type. So we can change the modulation index value and see how it will react. And in part 2, here we have the AC to DC rectifier. This rectifier is controlled. We have a controller that allows us to reach a voltage reference as well as the power factor reference. So in this case, we chose a 810 volts VDC ref, voltage DC reference, and we can see these are all the values that are the feedbacks of our model. So we can read that we reached 810 volts VDC as we want. So we can change it. For example, we want a 710 volts DC reference. We can see that we reach this value as well. We can also see it here on the scopes. So we have the three-phase grid voltage, the rectifier DC output voltage, the modulation index that is being used in order to reach this voltage, as well as the power factor here. So we can change also the power factor reference 0.8. And you can see that the power factor will change to 0.8 as well. It will follow the reference. Thank you very much. And if you have any questions, don't hesitate to ask me. So that was the fourth lab for the IGBT inverter rectifier. And now we will be adding the things that we used in the IGBT rectifier inverter, as well as what Wolf worked on, the DC-DC converter battery storage system in this circuit. So we have one part of it, it's the inverter, the DC-AC inverter. The second part, the second part is the AC-DC rectifier, and the third part is the DC converter battery storage system. So we have three situations. We can either, if the AC grid is on, the AC-DC rectifier is being supplied by an AC power, and then it is connected to the DC-AC inverter, which is then connected to the output load, supplying the output load. But if we lose the AC grid, so if we have a power outage, for example, it is the DC battery voltage in this part, for example, it is like this case, the battery is the one that is providing the power. So we're gonna see how all the circuit is working together in the following video demonstration. Hello, my name is Angel. In this video, I'll be showing you how to use the Uninterruptible Power Supply Systems electric courseware on HYPERSIM. So after opening the courseware, this is the circuit that we are working on. We can go to dashboards and then go to help. So this courseware is a continuation of the DC-DC battery storage interface, as well as the IGBT rectifier inverter systems. So as we can see, we have here the DC-DC converter for the battery, and we have the rectifier and the inverter that are used in the circuit. So we have an AC grid, which is connected to the AC-DC rectifier, which is supplying the DC-DC converter and the battery to charge the battery. And at the same time, it is connected to the DC-AC inverter, which is connected to the output load. In case of a power outage, the AC grid isn't supplying a power. In this case, the battery is the one which is supplying the power instead. So it goes from the battery to the DC-DC converter to the DC-AC inverter to the output load. I'm gonna run the model. So in this course, we're gonna be simulating both of these cases, when the AC grid is on and when the AC grid is off, and what will happen in the transition phase between the AC grid and the battery. So like in the previous coursewares, we have in this case the rectifier, the input of the AC grid is something that we can select ourselves, and we are controlling the rectifier's output, the VDC reference, as well as the power factor reference, and we can select a modulation index for the inverter. So MA is the modulation index. We can here see the voltage output of the inverter, the DC voltage at the input of the inverter here, the current output of the inverter, and the DC current at the input of the inverter. Okay. I will focus more in this case on display 2, because this is the new part. So here we're gonna simulate what will happen. We make sure first that the trigger is on. We're gonna simulate what will happen when we have a power outage. So this switch allows us to select if the AC source is providing power, so the LED is green here, or if we switch it to off, then we have a power outage and the battery will be the one providing the power. As you can see here, the battery is slowly charging, but if I click on this, here we can see that the battery is the one that is providing the power. As you can see, it's getting smaller every second. But of course, we are using a big battery, so it will take lots of time for it to empty out. And here we have the scopes of the three-phase load current as well as the line fundamental output voltage on the load. So we saw what happened when we had a power outage. We can also test what happens when the grid is back on again. And in order to study these two graphs, we can also, of course, every time change the DC reference, the power factor, the modulation index, and see what happens if we change those. Additionally, in order to study closely these graphs, after stopping the courseware, the model, it will save a recording file, which we can find in our directory. So here is the lab. We go to lab 5_HYPERSIM recordings. Here it is, this one. And here we can select which signals you want to see. So we have the line-to-line voltage, as well as the three currents on the three phases. We can select all three of them and put them in the same scope and run. So we are doing this in scope view. So as you can see, we saw the same results, and we can switch to the second test that we did by clicking here, and that's the second test. And here we can use, for example, cursors, look at two places at two different times and compare and see the delta. If you have any questions, don't hesitate to ask me, and thank you very much for watching.
Thank you very much, Angelo.
Hello, my name is Angelo. In this video,
And now we are the
Yeah.
question periods.
So I'm going to start by some questions that are raised. I have one of them. Thank you for the presentation. I have two questions. Assume that I have EMTP, so ECF extension project files of grid models containing power electronic system, and I need to run them in real time with HYPERSIM. First question, can I open and read with HYPERSIM ECF file created by EMTP? Who is ready to answer this question? Wolf, Angelo, Inosa?
The response is yes. You can open ECF file which were created in EMTP in HYPERSIM. However, while some components are compatible, the control part will not be compatible. You will need to draw your control scheme again in HYPERSIM, but the power component will be compatible.
Okay.
Like the switch model, like the physical component, all power components are compatible. But so if you have a network without control, the answer is yes, you can open and run. But if you have control, you will need to build the control again, because it is very difficult to make control block compatible from one software to the other one.
Thank you. Thank you for your answer. So that answers also the question number 2 of the same person. Can I edit this file and are they compatible? So the power part is, the control part is to be recreated. And so we thank you so much. We're going to move to another question. The precision of the thyristor control angle with 50 microsecond simulation time steps. So here we're saying 50 microsecond for a 50 Hertz system will be 0.9 degrees. How does HYPERSIM compensate for this error? And is there interpolation technique to improve the precision? I think this is this. Yeah, go ahead.
The question is quite specific, and it will require probably responding after the meeting, because that requires contribution from the technical HYPERSIM team. But my question is, my observation is that if the simulation is validated, that's the only thing that counted, because the way HYPERSIM proceed is not so relevant as long as the precision is demonstrated compared to actual devices. So I think they have interpolation, but as I mentioned, the most important thing is that it is accurate and completely superimposed with EMTP simulation.
And I'd like to add at this level that the topics of the 5 labs were suggested by you, Professor Kamwa. You did them already with SPS, and one of the things that Angelo and Wolf made sure to do is also to superpose and to make sure that the results are exactly the same obtained with SPS variable step at a very lower time step. So remind me, guys, what we're doing here is 50 microseconds, but when you compare to variable step SPS, we went way below 50. We went to something way below, I think 10 or 20.
Sometimes even 1.
Yeah, so basically all this was very well compared to references, and what we're showing is very precise. And I have another question. Now, what types of training modules are available in the OPAL-RT courseware, and how can they help user get the most out of HYPERSIM? Who is ready to answer that, or do I go with it?
Yes, you have to go with it.
You can go with that.
Okay, so for the time being, this is our very first.
I can only say before leaving you continue that HYPERSIM contains a lot of examples. Okay, so you can start there, and demo. They have a lot of demo. You can start there now. Continue, Daniel.
Exactly. And so what types of training modules are available in the courseware? This was listed by Wolf at the beginning. So we have the fundamentals of electrical engineering, really the basis with single-phase system, three-phase system, single-phase transformer, three-phase transformer, RLC, passive circuit, and they can be triangle, delta, or delta and triangle are the same, delta star, and so on, all possible combination. Then we have the power electronics, not this advanced one, also the basic one where we're covering AC to DC, DC to DC, and DC to AC. And the most complex with them is the 3-level NPC. We do have electric machines, synchronous, asynchronous. We do have motor drives where we're covering the drive of 4 different motors. And we do have the renewable energy courseware where we're covering different renewable energy components such as photovoltaic cell, wind turbine, batteries, and of course, putting all them together to have a microgrid. So we did already covered many topics, but the novelty is to have it in HYPERSIM this time. All the previous one I cited were under RT Lab, but it is our new one with HYPERSIM. So yeah, so for the second part, how can they help user get the most out of HYPERSIM? It is with this one that we can start working with HYPERSIM. And Professor Kamwa, correct me if I'm wrong, but you're doing now this fall term with your student at University Laval, you're using this courseware to start like using them with HYPERSIM. Am I right?
Yeah. I will be using the courseware for training my student, for speeding up the training. Before that, we were using SPS for exactly the same lab, but now we will be using HYPERSIM because it is more convenient, as explained by Wolf Peter at the introduction of the courseware. It is
exactly
more powerful, it is more stable, and at the end you can move seamlessly to real-time simulation from offline. By the way, you can do offline simulation with HYPERSIM, but the advantage is that at the end of your tuning your model, configuring your setup, you can move seamlessly to real-time simulation if the need arises.
Yeah, thank you. Indeed. And we have another question now. Okay, can HYPERSIM be integrated with other simulation tools or hardware? And if so, what are some common use cases? Who is ready to answer that? Wolf, do you want to go with this one? Yeah, can HYPERSIM be integrated with other simulation tools or hardware? And if so, what are some common use cases? Can you explain with which hardware, at least the one we're using for the courseware, if you want?
Sure. So, like HYPERSIM can be running in all of the OPAL-RT, I'll say all of or most of the OPAL-RT simulator. And in terms of integrating with other software, as Professor Kamwa mentioned, depend if you have a model on PSSC or Silent or other type of power system software, there are ways to take those models and integrate an HYPERSIM. Sometimes there are a few changes you need to do in order to simulate that model. You import you have your model on, let's say, PSSC, you can import it in HYPERSIM, but there are other changes you need to be done to make sure that the model when you're importing an HYPERSIM works properly. And you can also work with other type of, like, for example, we have model where we are running HYPERSIM with Exata. So basically for say cybersecurity and studies. So you are doing the communication, let's say using IEC 61850 standard to make sure that you have the cyber attack is taking place on Exata, and the model that you are studying, like the power system, is running an HYPERSIM. So that's kind of, it's not really core simulation, it's kind of the direction of core simulation. We can also do HYPERSIM with HYPERSIM, HYPERSIM with RT Lab. So you can do, in terms of flexibility, HYPERSIM offers a lot of flexibility on what you can do in terms of hardware and software for like integration with other software and hardware. So depending on the application and the needs. And if you want more details, we also have HYPERSIM training available that you can take So please feel free to contact Visible website or contact the support team for more detail about that.
If I can add something, there is also a filter for Dixilent. You can read Dixilent file with the recent version of HYPERSIM. The constraint remain the same like as with PSSC. You need to adjust your model slightly after reading it into HYPERSIM. You can, there is also a very nice tip in HYPERSIM which allow to import Simulink model in HYPERSIM. So you can build a Simulink block in MATLAB Simulink, and then use it without change in HYPERSIM. It is usually we call it hyperlink. It is a link between HYPERSIM and Simulink. And also Simulink, you should never forget that Simulink is really a real-time simulator. That means you can connect control and connect the control to the network simulation to validate if the control is working properly. And also because Simulink is a parallel computer, it can simulate a very large system, very quick, it is actually very difficult to beat HYPERSIM in offline simulation because it can split the network in multiple cores and speed up automatically without human intervention, the simulation. So that's something I wanted to add. But of course, it is better if you are interested to go to OPAL-RT website to find more resources.
Inasa, I have a question directly to you. For HYPERSIM and RT Lab, which one will you recommend to the students?
I think generally students will be tempted by RT Lab because they have prior experience with Simulink. So they will say, starting with RT Lab is quite easy. That's what they will believe. But unfortunately, it is not true if you have complicated system, if you have high switching devices, if you have power electronics. Very quickly, RT Lab will become slow. RT Lab will reach the limit. For instance, it will not be able to perform real-time simulation because the system is too complex for it. You will be unable to split in blocks. You will face bugs and actually they are not bugs. It is like limitation. So I am recommending to my student to move to HYPERSIM. That's what I am saying to them, because using HYPERSIM, you will have more something which is more professional, which can address both the network simulation and power electronic simulation and real-time simulation. So it is like one size fits all. So you will learn one tool and you will be able to perform a lot of different type of study. The only problem is that generally you will design your control in Simulink. But as I mentioned, it is possible to import a Simulink block into HYPERSIM. So you should not be afraid to start directly with HYPERSIM, even if you don't have prior experience. It is quite easy to learn, as you can see with this coursework.
I'd like to add to that two remarks. The fact that actually in RT Lab, we can do real-time power electronic simulation, even if the circuit is very complex. It is when we export a part of it to the FPGA. So the power electronic solver in FPGA, this is the EHS, electric hardware solver. And at that, once we export to FPGA, we can move really fast and we can even simulate in the nanoseconds. The second remark I'd like to add too is that we are working currently at OPAL to render the HYPERSIM solver exportable within RT Lab. So it's going to be sort of FMU in such a way that if you have developed something in HYPERSIM and you want to export it to RT Lab, you can encapsulate that, export it, and it's going to run in RT Lab. But this is the future. We're not there yet, but this is for all of you to know. So we're doing our best to make everyone comfortable, whether in HYPERSIM or RT Lab, and put the two forces, join the two forces together. There is one question: what is the integration method if trapezoidal method is adopted? How to suppress the numerical oscillations? I think this question at the one with the 50 microsecond and the compensation for 0.9 degrees. These are very technical one. If you are interested, we can pursue the discussion later on. You have our contact and you can ask us these specific questions.
But just like all EMT simulation, HYPERSIM is not different. They use companion representation of the circuit. So it is quite similar to EMTP. So there is no difference. If you know EMTP, then you know HYPERSIM solver. The only thing is that in HYPERSIM, there are some tricks to ensure real-time performance. Otherwise, the methodology is the same.
Okay. All right, so let us wrap it now. Thank you, Professor Kamwa. Thank you, Wolf. Thank you, Angelo. Very interesting webinar. And if for attendees, if you have more detailed questions, please do not hesitate to enter in contact with us directly. Thank you, everyone, and we're closing it now. Have a good day.
Okay.
Bye.
Bye. Thank you.
Thank you.
Bye-bye. Thank you.